Today we're going to talk about signal detection in theory. So this is very theoretical, and basically, more or less, I'm hope I'm going to leave everyone with the impression that I don't like the theoretical stories here. I don't like either of them, but they're very beautiful. They're two stories in theory, and they're both very beautiful. And the frequentest one is the Neyman-Pearson. I actually don't know how to pronounce Neyman's name, but anyway, the Neyman-Pearson lemma. And then the Bayesian story is the evidence, or what I call the fully marginalized likelihood, which Foreman-Mackey always enjoyed that it ended up with that acronym. We wrote some papers about that when Foreman-Mackey was at NYU. Okay, good. I'm going to set up the problem and then let's discuss. The problem I wanted to set up is a problem that is very dear to this institution. But there's two kinds of problems that are very there are two situations that are really, really heavily in play at CCA. One is the question, you're monitoring the LIGO data stream, you have the strain as a function of time, there's some wiggle in the strain. Is that wiggle in the strain a binary black hole in spiral, or even better, a compact object in spiral? Or is it just some noise fluctuation in the stream? That's one of the big questions. Another big question that we hope to be asking here very soon is, we've taken radial velocity measurements very precisely of some stars. Here's a star's radial velocity as a function of time. Is there a planet detected in this time stream? That's the Terra hunting experiment. So because we have both LIGO and Terra hunting, we are doing this all the time. So I'm going to use the Terra hunting example because I literally just came out of the call in which we were discussing it. So here we go. So here's time, and here's radial velocity. And what we've done is we've measured the radial velocity of the star at a bunch of times. And I'm not going to put units on this because this is very, very conceptual. And you have to tell me, given this set of radial velocity measurements, whether we've detected a orbital companion to this object. And that's the job. Okay, so this is the concrete question we're asking. So the concrete question is there an orbital companion? And now, you can also ask a completely theoretical question. The theoretical question is, I have data Y, and I have two models. And we're going to call the models H1 and, well, actually, we're going to call the models H0 and H1 because that's what they're always called. Remember, this is theory day. We're in theory land. We're only doing theory today. Two models, H0 and H1, and this model H0 has some parameters, let's call them theta 0, and H1 has some parameters, let's call them theta 1. There are parameters for these models in general. And then the question is, which of these models is the correct model to describe the data? And now, how are these two problems related? You can rephrase this question. This is a real world scientific question. You can ask a slightly more well-posed question, but we're going to see it's not very well posed. H0 is the hypothesis that there is no planet there, and H1 is the hypothesis that there is a planet there in some period range, say. I want a pretty well-defined. You really want these to be pretty well-defined hypotheses. This one is the star has a constant radial velocity, and this is like the star's radial velocity variations are caused by an orbital companion in such and such a period range. Right? Good. One more thing. We are going to do the very easy case, and this is actually really critical. That's called nested. What do I mean by nested? By nested, what I mean is that these parameters are a strict subset of these parameters. You see what I mean? So like in this case, in this incredibly simplified case, of course, it's horrifying. Remember, we're in theory land, so I'm just warning Megan not to get upset when I say that this hypothesis has only one free parameter, more or less, which is what is the radial velocity of this star. Of course, in reality, there's tons of other parameters here, which are like calibration of the device and weather correlations and all sorts of crazy stuff that might be going on in the data set. But let's imagine that the data are so clean. Remember, in theory land, the data is so clean that there's only one parameter of this model, which is what is the radial velocity of the star. And then here, there's many more parameters because there's what is the radial velocity of the star. Notice that parameter already existed. What is the radial velocity of the star? And what is the amplitude, period, eccentricity, orbital phase, and argument of perihelion of the companion. So this has of order 1 free parameter, and this has of order 6 free parameters, and one of the parameters is shared. The fact that this has a subset of these parameters makes these models nested. Or another way to say it is if I set the amplitude of the variation here to 0, this model becomes this model. Good? Simplest possible case. This is the best case for doing signal detection in theory. Good. Anybody want to say or ask anything? You're just like, no, I really don't, because there's so many things to open up here, because of course I drew error bars on those points and people could ask me, what do those error bars mean? That's going to matter, right? And then you can ask like, do you understand all the north sources going into this data set? And that's going to matter. Like lots of things are going to matter here. And of course people, yeah, anyway, good. Okay, good. So let's assume, because we're in theory land, let's assume that you have two likelihood functions. Actually, for both the Bayesians and the frequentists, no matter for the theory to be in play, for theory to work in this problem, we need two things. We need the probability of your data set. And this is like this, I should really have called this data set. So the idea is this is the whole data set. This is everything that you measured. And the way I'm thinking about this problem and the way terror hunting experiment actually works is we decide in advance what times we're going to take the observations. And that's part of the experimental design of the project. And then all the data points tell you is what was the radial velocity at that time, which we pre-selected. You see, so that means the only data here are the vertical locations of these points and their error bars. So just to put us like, remember that we always have like this incredibly long list of assumptions. And like the first assumption I'm just going to make is like, you know, this data is only, you know, only RV data. There's no time data, or the times are fixed. And we're going to later make assumptions like we know our errors and stuff like that. Or uncertainties, I guess I should call them. Sorry, my handwriting is so bad today. And various things. We're going to assume, like, we're going to end up assuming like a boatload of things here, just like in the first day when we were fitting a line. Okay, good. So for this theory to work, we need to be able to write down a likelihood function, which is the probability of the data, given the hypothesis 0 and the parameters 0. And we have to be able to write down the probability of the data given hypothesis 1 and parameters 1. Meaning we need these likelihood functions. And these are the likelihood functions that we use all in the previous times. And what do these likelihood functions look like? Well, if we know the uncertainties, and the uncertainties are Gaussian and all uncorrelated and all the usual stuff, this thing becomes chi squared. This is e to the minus 1/2 chi squared for one model, and this is e to the minus 1/2 chi-squared for the other model. So in the very simplest case, this thing is exp -1/2 chi-squared. And actually this is going to lead to, the Neyman-Pearson lemma is going to turn into something very clean with chi-squareds, because it's going to be about a ratio of these, which is going to be like a difference of difference of chi-squareds, which is, and people, I mean, the way I learned this stuff when I was a kid is it was about delta chi-squared. Good? Yes, go ahead.
Is this the case where the amplitude in the H1 model is quite bigger than 0? Or so like if the amplitude is very close to 0, but which means the companion is very small.
Good, great. So you have to say exactly what this model is. So what I said about this model is that it's just that there is a companion affecting the RVs. As you kind of are pointing out, if that companion is delivering a very small amplitude to the RVs, you won't be able to see it. But right now I'm including that in this hypothesis because I want the hypotheses to be strictly nested. So what that means is, so one way to think about it, you could think about it as H1 is that there is a big planet, right? But I'm just saying any planet, and then some of them just won't be detectable. And then we'll have what we call a false negative. The concept of false negative is about to appear. But right, and actually sometimes it's easier to answer these problems is if you specifically say that I'm only interested in companions that have an amplitude in this range, and that amplitude range is carefully chosen so it's detectable. Then life becomes easier in some ways, and then they aren't nested. Then it becomes a simple hypothesis test, and yeah.
When I'm thinking of this, I'm thinking maybe of the Weeks theorem, where you
yes, that's about to get harmed.
And in that case, you want the true parameters that you are checking in H1 to be far away from the boundary. That would be like 0. So this kind of machinery is right that it doesn't work if you're very close to the boundary.
That's right. Yeah, I mean, one way to say it is, we're in theory land here, but even in theory land, neither of these things are going to tell you what's happening when the amplitude is small. When the amplitude is very small, you're just done. There, you still have kind of information theoretic bounds. And we haven't talked about information theory yet, but in fact, this is the simplest result in information theory. This is and by the way, you can, from the Neyman-Pearson lemma, you can actually derive a lot of information theory from the Neyman-Pearson lemma, because Neyman-Pearson, you can think of the two hypotheses you're thinking about as just two different settings of the parameters. And when you do that, you get a continuous version of this thing, and then that becomes the Fisher information. And it all connects. But yeah, neither of these things are going to work when the amplitude gets small. But the whole point is, what's the smallest amplitude you can detect? That's kind of what we're asking. Good. Okay, good. I had a realization this morning that I think is completely useless. I was telling it to Tom this morning, and he was just looking at me like, thanks. Here's my realization, and I have no idea whether you consider this to be interesting at all. So here is the space of all possible data sets Y you could ever have gotten. So, right, so this is like this is a very high dimensional space, right? Like in terra hunting, if everything goes according to plan, we're going to have thousands of these measurements, like, of order 1,000, but maybe more measurements here. And so you can think of this as the 1,000-dimensional space of every possible set of measurements you could possibly have. And you can think of the decision making as being a boundary in this space. So there's a boundary in this space where if you're over here, you say H1. And if you're in here, you say H0. So you can imagine, you can think of it like this, there is a boundary in the space. And if you move the data points in certain ways and you cross this boundary, you're like, yep, there is a planet there. And if you're not across that boundary, then there's no planet there. Yeah.
But that boundary is like dependent on the confidence with which you want to claim detection.
It does. You are going to say, so like terra hunting, you could imagine, I don't know if terra hunting will do this, but you could imagine terra hunting says, we are a 7 sigma project. So, but good.
I mean, good, yeah, there's nothing absolute.
No, there's nothing absolute here, and there never is. By the way, the most disgusting thing about all of this stuff is that nothing ever tells you where to put the boundary. There's no theory of where to put the boundary. We're going to talk about the boundary in a second, and you'll be able to talk about it in terms of sigmas or in terms of probabilities or whatever. You're going to be able to talk about it a lot of different ways, but nothing tells you what you should do there. And that's very intuitive, right? And the particle physics community chose 5 sigma a long time ago, and they just use 5 sigma. And it's worked out very well for them. That's been a good choice. The medicine community chose P of 0.05. And that's worked out very badly for them.
How many sigma is that?
It's like 2.
Yeah. 2 sigma in particle physics, people love.
Yeah.
Just like
That's
it's a
correct.
fluctuation.
Yeah.
I hope they don't make medicine based on that.
Well, the thing that protects medicine, no, but medicine is protected by a different thing. Well, medicine is protected by 2 things. One thing is if you make a mistake in medicine, people start dying around you.
Yeah, sure.
And then you notice. So that's one. And the other is that the P of 0.05 trials that they get inspire more trials. They don't just release the drug on 0.05. They do 0.05 gets them another trial. And if that hits 0.05, that gets them another trial. And if they get through all the trials, then they're good. And a string of 0.05s is actually very strong.
That's the same of what we do in particle physics, though.
Exactly.
You have
It's
an
exactly the
anomaly,
same.
then you make a better.
Exactly. You
experiment,
keep
like
going
go
and
from
then
2
you
sigma
hope
to
it builds
5,
up.
yeah.
Exactly. It's just that we formalized it by combining all the data, whereas they formalize it by doing repeated trials. Good, great. Anyway, there's a lot of different ways you can draw this line. I'm going to talk about 2, but there's lots of heuristic things you could do here. And in fact, you know, like you could think about really dumb things here. For instance, you could ask, you could say, well, is the root mean square variation in my points larger than I expect? And then if it is, we've got a planet. I mean, you'd be fired. Well, if you have academic freedom, you can't be fired, but it would be a bad choice to just go on the RMS of these points. That would be a bad choice. But notice that is a choice you could make, and that choice would make a different boundary here. So there would be a boundary that's like this, which is the boundary, which is just like, what's the RMS of the points? And you would, if you did that, if you just looked at the RMS of the points, there would be a bunch of things here where there really isn't a good argument that there's a planet there, but you nonetheless announced. And there would be other planets there that you wouldn't actually get. You know, like, and then if you're a Bayesian, you'll draw yet another boundary, and we're going to talk about that boundary in detail. So then there's another boundary you might draw if you're Bayesian. And like you're going to draw different boundaries based on different choices about how you think about this problem. Neyman-Pearson lemma very specifically, chooses a one-dimensional family of boundaries, of which this is one, and the Bayesian evidence chooses another one-dimensional family of boundaries, of which this is one. Good. Okay, great. And then the claim, the Neyman-Pearson, okay, so I'm not going to be very specific about Neyman-Pearson because I don't totally understand it, but Neyman-Pearson says, and I pronounce it a different time every way, it says the uniformly, now my brain just got erased. It's the uniformly what? It's the, uniformly most powerful test. The uniformly most powerful test. Okay, so what's the idea of the uniformly most powerful test? The idea is you want to detect all the planets you can detect. So you imagine a world in which there's many repeated experiments in which there are stars that do and don't have planets, and you observe them all like this. And what you want is to minimize your false negative rate. So what you want to do is you want to minimize false negatives. And what do I mean by false negatives? You want to minimize the times you go, nope, no planet there, when there was in fact a planet there.
Isn't that false positive?
No, that's false negative. We're trying to minimize saying, nope, no planet. See, that's a negative result, but you're false
Because that's that.
because there is a planet there. See, it gets confusing what's false positive and false negative. It's a little bit, but the way to think about it is this is the positive result. This is the result where, like, Megan's on CNN.
And
And
I'm wrong. Would that false positive be worse though?
Good. So
Right?
prior to Neiman Pearson, the standard thing was just was to minimize false negative,
Positive, right?
positive, to minimize false positives. The previous to this, the goal was to minimize false positives. And then what you do is you do a classic p-value. Then you only have one. We're being frequentist right now. We will get Bayesian. Don't worry, Bayesian is coming. And I'm going to be very mean to the Bayesians. But in prior to Neiman Pearson, there was just H0, and you're just asking, is it ruled out? And so in a lot of these medical tests that we're talking about, when they say they have a p-value of 0.05, they're just saying at p-value of 0.05, they can tell that the medicine does something. They can't, it doesn't do nothing is really a better more accurate thing to say. So when they say they have p of 0.05 in medicine, they're saying this is ruled out at the 0.05 level. Or there's in 0.05 of all repeated experiments in which there was no effect, would we have gotten the deviation from the expectation this large or something. It's like, it's very hard to state actually what a p-value is, but technically a p-value is just saying that this is ruled out. And there is no second hypothesis. The thing, historically, the thing that Neiman and Pearson were doing was saying, but actually you don't just care whether this is ruled out, you care whether this is ruled in. And so they switched the focus from false positives to false negatives, because they want to make discoveries. But you're right that if you really want to be conservative, you're just trying to get rid of false positives. That's why medicine uses that approach,
Yeah.
because they really want to be conservative.
Yeah, I just think of like an example where like I would be more concerned in claiming a matter detection. Than
Yes.
making a mistake and like
That's right.
saying that we didn't find it, right?
That's
It's
right.
like,
That's
in
right. So-
physics, I would be more concerned.
Great.
but
And so you
like-
can think, and we live in a world where, like, in our cosmology lives, we live in a world where lambda CDM is really well established. Now you want to find a deviation. We don't really know what the form of the deviation is. So we're really asking whether the data are consistent with the null model. We're not asking whether a different model is preferred. I mean, sometimes we are, but the most conservative thing to ask is whether this model is okay. And to our great concern, it is. Terrible. Yeah.
Don't you have to consider both false negatives and false positives? Because you could never have a false negative if you just always predicted there's a planet, right?
Exactly. So good. I'm gonna say a word about that in just a second. Yeah.
Great to see it.
I think I'm a little confused when you're saying the p-value of 0.05 is around 2 sigma and it is bad. Is like one solution to minimize, to make the p-value smaller.
Yes, that's essentially what the particle physicists sort of do. Right? They, when they say, like, we found the Higgs at 5 sigma, they're saying they make the p-value of they basically considered a world where you have the standard model without the Higgs and showed that that was ruled out at 2e minus 6, whatever it is, 2e minus 5, whatever it is. They basically, it's a p-value that's just very, very small. Okay. Yeah. Good. Right. You can ensure that you never have a false negative by just setting your threshold to 0. So this is actually minimize false negatives at some rate, at some false positive rate. So one way to think about it, remember I said that each of these things is going to give us a one-dimensional family of these things. You can think of that one-dimensional family as setting your false positive rate. If I move this boundary this way, I'm going to get more false positives. If I move it that way, I'm going to get fewer false positives. I've carefully drawn these two lines so that there's the same number of same rate of false positives for those two models. And now the question is, and so the Neyman-Pearson says this is the uniformly most powerful test. Yeah.
When we talk about p-values and sigma, you're assuming that something is Gaussian?
Yeah, we're not there yet.
Okay.
But yes, we haven't actually written down anything yet, but as soon as we do, we're going to find, as soon as we write down anything specific, we're going to find that we have to add to this list of assumptions. Oh yeah, and traditionally in this class, I highlight assumptions. Okay, good. Good. Okay, great. Let's just state the Neyman-Pearson. So Neyman-Pearson says, let's see if I can write this down correctly. So Neyman-Pearson says, I'm always encouraging people to think in terms of log probabilities, not probabilities. So let's work in log probabilities. So it's going to be, we're going to construct a statistics D, which is the log of the probability. I'm already wrong. I'm going to write it in a stupid way, but it's very, very clear. It's the max over theta 1 of the probability of the data given H1 theta 1 minus the max over theta 2 of the probability of Y given H2.
Log, yeah.
Logs, god damn it. Lon. Oh yeah, and then we learned that I'm the only person who says lon. So it's the log probability minus the log probability. It's the difference of log probabilities. And we're going to set the threshold. We're just going to set a threshold on this. But I want to make a comment here. If you look at this, you see how this statistic is always greater than 0? See why it has to always be greater than 0? The reason it always has to be greater than 0, and this is an important point, and this is one of the reasons the Bayesians don't like it. It always has to be greater than 0 because this model contains this model within. Sorry, this is supposed to be zeros. Sorry, I'm just completely in a mess today. So stressed out by the Terra hunting experiment this morning. I lost my ability to think. H0, comma, theta 0. Good. Better. This contains this model within it. Therefore, this model always has to be better at explaining, strictly non-worse. This model always has to be strictly non-worse at explaining data than this model, because the models are nested. Good. The Neyman-Pearson lemma actually applies to non-nested models too, but the detection questions are almost always nested. And so in this nested thing, this thing is always greater than or equal to 0, and it's never really 0. It really is always greater than 0. Yeah.
Todd, I missed the part where you drew the parameter space with H0 and H1. So when you say that, you mean H1 is included in the entire model parameter space.
Oh, good. This plot is a really weird plot, and this is the plot I was hesitant to draw because it's more confusing maybe than useful. This is the plot, this space is not the parameter space. This space is the space that the data can live in.
Okay.
And so in some places in the data space, you say, yes, there's a planet. In other places, so this is like the 1,000-dimensional space of all the values of all our RV measurements. So this is a really weird space. And I didn't draw the parameter space. I just said in words that this model just has the radial velocity of the star. And this has the radial velocity of the star plus the amplitude, period, eccentricity, phase, and argument of perihelion of the planet. So, and then these are our data. So one model is like, there's a straight line here, and the other thing is there's a elliptical or whatever, eccentric orbit affecting this.
David, I have a
yeah.
question.
Amy, yes.
So your Y space is under every possible parameter value as well?
Well, it's sort of every observed data set you could possibly get. Yeah. It's worse than that.
Yeah, under any combination of parameter values.
And any noise draw.
Yeah, okay.
Yeah. So this is a really extreme. That's why this plot is not a very useful plot.
And in reality, there's like different, like true underlying models that are different to either hypothesis that live in the space of the possible.
Right. The data space can contain any possible hypothesis you could ever make up. So in fact, there's also boundaries for tons of other models in there. And there's like, yeah. And there's like directions in the space that are bad and impossible and weird and all these things. Yeah. Yeah. So this is a really weird space. It's not clear that's a useful space to think about, but sometimes it's useful to think about it. Okay, now, so basically the Neyman Pearson says, so the advice of Neyman Pearson is choose a threshold, and if D is greater than T, you say H1. That's Neyman Pearson. So you construct the difference of log likelihoods at their maxima, and you choose a threshold and you go, cool. And if you want to know what threshold to set, you do simulations. Suck it up. And you might think, oh, but how do I do simulations? Well, by construction, you claim that you know these models, right? If you know these likelihood functions, well, then you can do simulations because these are probability distributions. You can sample from them. And so and we never do this, right? With MCMC, you never sample in the data space. You're always sampling the parameter space, but you can sample in the data space. In fact, you can without even a prior. You can sample in the data space. If you just tell me parameters, I can give you possible data sets you might have gotten, and same thing over here. So frequentism is like a closed system. If you can do this Neyman Pearson test, you can also simulate the data that you need to check your thresholds. It's good. No priors. No priors. No priors were harmed. Pretty good. I actually strongly recommend this in a lot of cases. And I will recommend that the terror hunting experiment use this. Actually, the only issue is that in the terror hunting experiment, there's going to be noise sources we don't understand. And so these parameters will include horrifying parameters of noise sources we don't understand, which is bad. But that'll just, I think, will just weaken our test, but won't make us wrong. Yeah.
So does this mean that like, does this mean that in practice?
Actually, we have ceiling mics, so it's actually, the audio is okay. But anyway, but it's fine.
So in practice, like we sort of brought up Gaussian, like having a Gaussian likelihood before. Like as long as, I guess, if you can draw from the likelihood, is that more important than actually it being Gaussian or something for this? Because in lots of like particle physics experiments and stuff, they have to have like numerical likelihood.
Good. I'm about to write down what this looks like when you have everything's Gaussian and your data points are independent and all the things that Gus just indicated. So I'm about to write that down, but you're right. All this really requires, to do this, it only requires kind of two things. One is that you can compute this function. And of course, if you're a cosmologist these days, you can't. So sorry, this is out. But the first thing is, can you compute this function? And then the second thing is, can you sample from this function? If you can both compute it and sample from it, the world is yours. You can do anything, and you can figure out the threshold, and you can show that this is the uniformly most powerful test and everything. So, and it has nothing to do with the form of the likelihood. The only issue is that most likelihood forms that aren't Gaussian are hard to sample from. But one that is easy is Poisson. So the particle physicists do this with Poisson because they believe for very, very deep quantum mechanical reasons that the different events in LHC are independent Poisson draws, which is actually a very good model for the LHC. Like if that isn't true, we're really in trouble. Then there's like a God. We live in a simulation. Like really that has to be true. Okay, good. So I said this here that like these will become this in the case that these log probabilities will become chi-squareds in the case that you're not just that you know your uncertainties, but they're Gaussian and uncorrelated. So if we go Gaussian and uncorrelated, so if Gaussian uncorrelated, this thing becomes chi-squared. It becomes like the minimum, remember chi-squared maximization or probability maximization is chi-squared minimization. So it becomes the minimum over theta 0 of chi-squared 0 minus the min over theta 1 of chi-squared 1. So D becomes exactly 1/2 this thing. There were some minus signs, halves, this thing. And so this is just delta chi-squared. And by the way, this delta chi-squared is always positive. Why? Because this model is simpler than this model, so this will always have worse chi-squared. So you have, this is delta chi-squared. And we're kind of used to delta chi-squared, it's a good thing. And like 5 sigma is like a delta chi-squared of like 25. So you can talk in terms of sigmas once you write down this expression. So that's also really nice. You can just talk in terms of sigmas. Good. Everyone good? That's Neyman Pearson. Yep.
Will you comment again on this like most powerful test? Like now that we have the mathematical language, what actually?
No, totally not.
Like, I'm surprised the statement is not dependent on like the priors of theta or something. It's completely independent.
I believe, yeah, oddly, it does not depend on it does not depend. That's what the uniformly,
Right.
In uniformly most powerful test means. It doesn't depend on what the distribution is of planet amplitudes. And most Bayesians right now are going crazy, and they're going crazy for 2 reasons. One is that you can't optimize, you'll never know these parameters accurately. You must have to do some kind of integral over these parameters, god damn it. It turns out I'm not going to agree with that, but I can see why this is upsetting. Why would you be minimizing over these parameters instead of integrating over them? And remember, we talked about sometime in the past, like frequentists take derivatives basically, and Bayesians integrate. Once you want to integrate, you have to be a Bayesian. So people want to integrate over this. So that's the first thing. But then the second thing is, there's a feeling that your confidence must somehow depend on the distribution of planets that are actually out there. Like if God came down to the earth and said, there are no planets, then you would know you should set those thresholds really high because there aren't any planets, and you will be right with God if you say there's no planets. Yeah.
Just to make sure where I'm supposed to be. So functionally, you set this up and then you do the optimization on getting D as big as possible. Like, I guess I just like, there's all these you've got your set of data, you've got all these parameters that you do not yet know.
Yeah.
Am I then sampling in parameter space to find when I get to like what is am I just trying to find the largest value of D and then saying that's my best estimate of the parameter? Or am I finding the largest value of D and that tells me, okay, I should now fit it normally as if I've now decided it has a planet.
Good, you're
So I
not,
should do separate
good,
inference.
good,
Is
good,
it a two-stage thing, one
it's a
stage?
two-stage thing,
Okay.
and you're not trying to optimize D.
Right.
Because you could optimize D by just taking the theta parameter, the zero parameters in some weird direction that's stupid. So what you're trying to do is you're just trying to say, what's the best I can do with my null hypothesis? So you optimize your null hypothesis alone and just say, what's the best I can do at explaining my data with the null hypothesis? And then I optimize the crap out of my positive hypothesis. And what's the best I can do with my positive? And then I just difference them.
Oh, so you're just calculating one number.
One number. D
Okay,
is
so
a
this is
single
like
number.
once. You're
You
calculating
do it
one number
once.
once.
Once for
Okay,
once.
that totally was not
That's it.
clear. I'm glad we had
Yes,
this little
sorry, I'm
chat.
glad you asked the
Great,
question.
good, okay.
That is what exactly, and Megan's laughing because I said sorry.
David,
Yeah. Oh, Will is on the phone. Yes.
yeah, I'm coming out of the sky. Maybe 2 sentences in answer to Constantine's question.
Yeah.
In this context, the uniformly most powerful means for all tests with a given false discovery rate.
False positive rate.
Yeah. This test will maximize the true discovery rate.
Yes, or minimize
Minimize the
the
false rejection rate.
Good, very good. And I did say that at the beginning, but I didn't say it quite as clearly as Will just said it there. So right. And so, as I said, both of the things we're going to talk about today, there's a threshold. Here, there's this threshold T, and you can modify the threshold as you modify the threshold. And remember, we have total command over this problem, so we can simulate data sets, both with and without planets. And what this says is that if you set T to minimize, to set a certain level of false positives, you want to minimize false negatives. Very well said. That's why we pay Will the big bucks.
Can you comment on the complications that arise when you don't know the error bars? Because I assume in the
Yeah.
error hunting experiments case, you're
Yeah.
not going to know the uncertainty
Absolutely.
rate of losses.
Absolutely. All I'm going to say about that is that, and by the way, next week, this class will be an introduction to Gaussian processes, which is one of the ways to parameterize some of the noise you don't know. Good. So that we're going to literally be talking about that next week. Andy Casey is leading it next week. All I would say is that if you don't believe your uncertainties, or you think there might be additional noise sources, you have to add them as parameters here. And if you want to stay nested, you also have to add them as parameters here. So one of the ways you can do this, which is actually probably one of the components we're going to do in terra hunting, is we're going to add some kind of horrible mixture of Gaussian processes into these parameters. Plus maybe even some calibration issues with the device. We don't know. We don't know what the things that we're going to be worried about are when we're going into this stage. But whatever we're worried about is going to go in here parameterized. And it will also go in here parameterized the same way so that they stay nested. So the dumbest thing is, imagine you just thought they underestimated your error bars. Then you could just add an adjustment that you add to every error bar in quadrature, say. And then that just becomes one more parameter that goes into the fit, and it goes into both sides. And by the way, we do that in the Yoker. So Adrian and I have this project called the Yoker, where we try to find automatically all the binary star systems in the Apogee data. And when we do that, we have a parameter which is excess variance. And that's part of the likelihood. Actually, we do Bayesian. There we're being Bayesian, which I say you shouldn't do this. What I'm about to say next, I think you shouldn't do, but of course we do all the time. Because that's our lives. Good. Good. Okay, great. And actually, the thing that's cool is in that. By the way, when you believe there's additional noise sources and you believe that they're additive and they're but they might be correlated Gaussians, then this actually stays just as simple, right? It's just that now chi-squared is written using a covariance matrix, which involves a kernel, but it's still basically chi-squared. And actually, things are just as easy in that case, actually. You just have to, you get some log determinants added in. Determinants of matrices up here, because right, when you don't, when you, really the log probability is really x of, sorry, apologize, is really x of minus 1/2 log determinant of some covariance matrix and kernel matrix or something like that, right? If you have a Gaussian process. So you have chi-squared, but then you get some determinant of some matrix added. So, but other than that, everything stays the same all the way down. So you would just have, this would just be this chi-squared difference plus a difference of 2 determinants. I say just, but actually when you have 1,000 data points, it's really hard to compute determinants. That's something we work on in CCA and CCM. CCA and CCM work on fast determinants. So if you have determinant issues, come talk to us. Okay, good. Now, we're obviously running out of time, so let's get Bayesian. So if you're a Bayesian, obviously if you're a Bayesian, you would never optimize these parameters. That's absurd. You don't know the parameters. In fact, the parameters that are always represented by a probability distribution that represents your beliefs, because you're subjective Bayes. And I just want to remind you that the proofs of Bayesian inference, a lot of Bayesians are like, Bayesian inference is proven to be best, most rational way of reasoning about things. Correct, I agree. Those theorems are excellent and they're correct, but they rely on you having beliefs. You're going to need to have beliefs in a few seconds. And sometimes I don't have beliefs. In fact, we're doing Terra hunting because we don't have beliefs about what fraction of stars have planets at different periods. Yes?
Do you think this is because you don't have beliefs, or you don't explicitly formulate your beliefs? Because maybe you can map like the frequentist approach to the Bayesian approach, and then you actually find you implicitly putting beliefs in. Is that possible? Or like, what does it mean to not believe anything, right? Like that's hard.
If you didn't believe anything, you wouldn't do the experiment. Sorry.
I mean, it is
Sorry.
true. It is true. The funny thing is, if you believe good, it's both the case. And if I had a strong belief about the distribution of planets around other stars, I wouldn't do the experiment because I'd already know. But it's also true that if I had no belief about planets around other stars, I also would not do the experiment. So it's a little upsetting. I'm upset. Anyway, what you do if you're Bayesian is you compute the integral, which I call the FML, the fully marginalized likelihood. This is the integral of P of y given H0 and theta 0. And I'm going to integrate it over theta 0. But in order to do that dimensionally, that means I need a probability distribution over theta 0 in H0. So if my null hypothesis is H0, it has these parameters. Within this hypothesis H0, I must have beliefs about the distribution of these parameters in order to do this integral. If I have those beliefs, I can do this integral. And then you do the same thing for H1. P of theta 1 given H1, D theta 1. And the ratio of these, and I think because I wrote them the wrong way to the -1, the ratio of these two integrals gives you a statistic, which we could call D. Maybe I should call it B because we're being Bayesian. This gives you a statistic, and you can use this statistic with a threshold to compare the two things. And this just gives you a likelihood ratio. Notice this is a likelihood ratio. Why? Because when I do this integral, it integrates out theta. So you can think of this as being, you can think of B as being the probability of y given H1 over the probability of y given H0. You see how, because you've integrated out theta 1 from this, So the theta 1 goes, and you've integrated out theta 0 from this, so the theta 0 goes. So this ratio inverted becomes this one. It's just the probability of the data in this hypothesis over the probability of the data in that hypothesis. And then if you really want to go to town as a Bayesian, you can multiply those by priors on the ratio of these probabilities, of these, the prior on the two hypotheses if you want. But even better, you can put in utilities here about like how famous you'll get in the two cases, and then you can do decision theory and maximize the long-term discounted expected value of getting the Nobel Prize. You see, this is the input you need to do anything Bayesian. Good. No one in here objects to this because you're all such Bayesians. Obviously, this is the right thing to do. Duh. What else would you do? So why don't I like this? The reason I don't like this is that when you're doing an experiment like this, so let's think about the case of the target for terra hunting is planets that have periods of around a year around stars that are similar to the sun, right? It's terra hunting. We're trying to find Earth. We're trying to find not Earth 2.0, but other Earths. And so you can imagine asking, like, one of the things you might want to know is the velocity amplitude in kilometers per second. What is the expected velocity amplitude of planets that have periods around 1 year? Okay, and the Earth, by the way, the Earth around the sun is making something like, is it 13 centimeters a second? 9, brutal. 9 centimeters per second is what the Earth does around the sun. And now when you do this integral, right, you're going to have to integrate over all possible values for this velocity amplitude. What do you think this distribution is? By the way, the smallest planets we found are here around 90. So the smallest planets we found are here and up. And also they're at shorter periods. So we have nothing anywhere near this dashed line that we've ever observed. But to do this integral, I need to know a distribution here. I have to write down a distribution here. And I don't have to write a distribution of distributions. I have to write one distribution to do this integral. See how that's impossible? I just do not have specific enough beliefs about this to do this integral. Of course, people do it all the time. This is done all the time in the literature. Decisions are made on basis of this all the time, and I believe every one of those decisions is actually wrong. The one place where it might be right is in LIGO, because LIGO has now measured enough things that LIGO can start to have an opinion about this. But I don't have an opinion about this for terra hunting. So we know something about this function over here, right? But then, like, what does it do in here? Does it do that? Does it do this? Does it do that? Does it do this? We have no idea what it does inside of somewhere like this. We have literally no idea. And you can see this integral is going to depend incredibly strongly on our decisions here. Yeah.
I mean, could you not do some sort of like prior sensitivity test where you inject a whole bunch of these and then build some distribution of Bayes factors and look at how?
Absolutely. So the right thing to do, which by the way, most of the papers in this area don't do, but the right thing to do is to do a prior sensitivity test over every prior you might write down here. Then you will find that you basically don't come up with an answer that's better. Usually it comes out to be worse than Neyman Pearson. So you could have just used Neyman Pearson and actually got a decision. But you'll find, because you'll find that there's extreme things you can put in here that will just always prefer the null. Yeah.
Okay, so that reminds me of something that we do in astroparticle that, though I don't think it's wrong, and you can sort of like quantify your uncertainty very easily, is that we don't know what's the dark matter profile in the galactic center, right? That is not good reason enough to not look for dark matter, right? You just have like 3 different profiles, some standard, some optimistic cusp, and some like chord.
Yeah,
And these are like three wildly different options so that you can do Bayesian and just
yeah, I mean,
quantify your uncertainty.
yeah, I think the right thing to do, like if you want to be Bayesian, you are allowed to be Bayesian here. But if you're going to be Bayesian here, you have to think about some extreme models. And notice that if you think about this extreme model, you're always going to decide that you don't have a planet there. But that might be true. This might be the correct situation. If you put in this model, you're going to kind of always decide that there is a planet there. And then you're just gonna have to say, our belief about this planet is conditioned on this prior. Yeah.
I'm a little confused because I thought at the beginning we were talking about like H1 versus H0 as models for like an individual data set of RVs.
Yes, this is one data set of RVs.
Okay, and I guess like this is just all of them combined, right? Now we're talking about the like kind of static H1.
No, it's literally the case that in order to do this integral, even this is just one data set and one hypothesis, in order to do this integral, you have to have a belief about the distribution of the parameters. And so this is my belief. This is a statement not of the data, but of my belief, of my prior belief before I made this observation. And frankly, on Terra Hunting, don't have a belief about it. I truly don't. We do have some knowledge about planets out here, although not at these periods, but still I could probably develop some kind of belief out here. But I definitely don't have any belief in here. I just don't. The only data point I have is that we live on a planet of this type. Yeah.
But maybe I misremember, but isn't the Newman-Pearson test like a subset of that where you assume a delta function for beta 1? So maybe
No. So again, most Bayesians believe that the frequentist tests are somehow a Bayesian test under some assumptions, but that's not true in this case.
But when I substitute a delta function for b theta 1, don't I get exactly the above expression?
No, because if you do the delta function, but no, because that delta function is conditioned on the data. So no.
Right. I mean, yeah, you're kind of retrospectively, but like,
but that isn't a test then. You know what I mean? Like you're right. You can, in principle, you can say that, but actually that wouldn't be an executable situation.
Right, but do you agree that like if the Bayesian says like, oh, I've looked at the data, I pick the best beta, and I plug that in, I would get Pearson-Newman, right? Or
well, not really, because it has different units and stuff. Like, I don't know. I think you're definitely like, yes, you can say that, but I don't think it's really theoretically justifiable.
No,
I think you really have to decide where you're at. Yeah. But they are related. They're definitely related. And by the way, the two things are very related because this ratio is here. Notice that ratio is there, which is the ratio in Neyman-Pearson. So they're very related. It's just that you've taken them through integrals. And one of the big issues is that this integral has a different number, is a different dimension than this integral, right? This had one free parameter, this had 6. So they're like different spaces that you're integrating in. And of course, the Bayesians love this because it represents parsimony or whatever, but it's very, very sensitive to these decisions, which are literally why we're doing the experiment. Yes.
Yes, I was actually reading a little bit before this. There's a thing called Lindley's paradox, which is basically exactly related to this.
Yes, Lindley's there's a bunch of paradoxes. There's so much written about this problem, by the way. This is enormously written about. There's almost journals about this problem.
Yeah.
And the standard one is you have a pill, and was it effective or not effective? And you can really get into paradoxical situations where, and there's both paradoxical situations where the Bayesians make bad decisions and paradoxical situations where the frequentists make bad decisions.
So in the Lindley one that they were arguing about in the 30s, they were saying that like if you take, in this case, like uninformative priors on H0, on H1 and on theta 1, so on the things you're trying to detect, in general you'll end up very pessimistic in the base factor versus you would have claimed the detection, and it's because of the extra volume that you get in the integral.
Good. Hold that thought for just a second. This is a 6-dimensional thing. This is a 1-dimensional thing. So now imagine two people do different integrals, and one person sort of uses slightly broader priors than the other, but they're kind of similar, like sensible decisions. Like this one is slight broadening to the 6th power. So this one gets killed. So basically, this hypothesis gets killed by the person who's just like, well, what if it was like 20% bigger? And then boom, then all of a sudden you're because it's taken to the power of the number of parameters. Good, keep going.
I guess what I was gonna say is that that leads to the Bayesians being pessimistic about their
Often, yes.
detections.
Often, yes.
If they were, under this assumption that they're
Yeah,
using more
That's
uninformed
right.
priors and stuff.
That's right.
So I guess like, I'm not sure whether it's something to necessarily be like worried about that people over a long time are gonna come up with long term are gonna come up with the wrong thing.
Good. It depends what you're worried about. But there are some situations where, yeah, I mean, yes, it depends what you're worried about. Sure. But I mean, sometimes showing the null is the discovery. Like, it's not always the case that the positive is the positive. You know what I mean? But I agree with that. Yes. In general, the Bayesians will be, a conservative Bayesian will be much more conservative than a conservative frequentist. That's correct. And it's related to the fact that if you have a prior that there aren't planets in this area, you'll never detect a planet in that area. So that's conservative. It's conservative to say, I don't think there's any Earth-like planets. Terra hunting will always find nothing, and then we'll always find nothing.
Yeah, pure Bayesian, we've never found a hot Jupiter, right? Because back then we didn't think hot Jupiters were physically
And that's
possible.
good. The hot Jupiter case is such a good example because both the California group and the Geneva group had data on the star.
Yeah.
And the Geneva group discovered it and the California group didn't discover it because the California group never would think to go down to 6 days or whatever it is. I don't remember what the period is, but they just weren't searching below like 2 weeks period or something. So they missed it. Nobel Prize, baby. We are out of time. We were going to return to the subject, and I'm going to say what I think you should do when you're trying to detect a signal, which will not very much use either of these.